Hello everyone. My name is Nicholas Sedlmayr, and I'm gonna tell you all about an unconventional topological transition in a self-organized magnetic ladder. Yeah, this is work done here in Lublin by myself, along with my colleagues Domański and Kobiałka, and Maśka from Wrocław University of Technology. And you can find the details of what we've done in this recent PRB. Okay, so what we're looking at here is this kind of now very popular and well-known field of symmetry protected topology. Okay, so we have this kind of well-known classification of all the different kind of symmetry protected topological phases that we can have in topological insulators or topological superconductors. The example we'll look at is actually a topological superconductor. And they're classified by these three different possible symmetries that we have to take into account: time reversal symmetry, particle hole symmetry, and chiral symmetry. Okay. Now, to kind of introduce what's kind of unconventional about the version that we will do, let's first actually look at what the normal topological phase transition is like. So here I just pick a model. This is actually a model on a kind of hexagonal lattice. You see I have kind of hopping terms, Rashba spin-orbit coupling, a Zeeman field, superconductivity, and all of these ingredients together create a topological superconductor. Right? I picked this model actually just because it's one that I've worked on, and in fact it has a very rich phase diagram. Okay, and we can calculate the topological invariant for this. Right? That's the second Chern number, or TKNN invariant, given here. And actually, if we do that for this model, here's an example of a phase diagram for a particular Rashba spin-orbit coupling. And a particular superconductivity parameter, but you can see you get all these different topological phases. Okay, now to go from one topological phase to another, of course, what we have to do is close the gap, right? That's the idea of the protected topology. And the other kind of interesting thing, about these topological systems is the so-called bulk boundary correspondence. No? So this topological invariant we calculate sort of maps directly then to the kind of number of modes that exist on the edge of the system. It's one of the reasons these systems are of such interest. So let's actually check, this in this case here. So here I have, I can look at various different kinds of boundaries of a hexagonal system. So here's some examples for zigzag and armchair. And here I have a phase where the invariant is 4. Okay, and if you count, you can see indeed there are 4 counter-propagating modes in each case. If I close the gap and I open it again, I go to a different invariant here, -5. I change the number of edge modes, right? But I have to close the gap and open it again to get from one of these to the other. Right? The only other option to change the topology is actually to change the symmetry. But then if I change the symmetry, I change the topological class of the material as a whole. Okay, now with that kind of reminder about topological superconductivity aside, let's now look at the model that we're interested in. So this is a kind of simpler model. It's just a ladder, okay? This ladder of kind of magnetic atoms. And we will place this on a substrate, kind of not shown here, which is superconducting. So we have some kind of proximity-induced superconductivity. And we allow the directions of the local moments of these atoms to vary in various different ways, right? So actually, in the two pictures you can see at the top, you can see that there's one example where delta Q is the angle between the excuse me, between the magnetic moments on each rung of the ladder. Okay, and they often actually we find that they are in 0 or pi configurations. We also allow then the kind of pitch of the change along the ladder to vary. Okay, and these are parameters we will find just by trying to find what the ground state of the whole system is. Okay. So here indeed is exactly that. So we have a kind of pitch Q and a delta Q, which is the difference between the rungs. Okay, and otherwise it's just a typical chain of atoms. Okay. So for each point in parameter space, as I say, we can find the ground state configuration in the spin order. So here's some examples. These are cuts through for different chemical potentials. And shown in our 2D plots of delta Q and Q, and this is the energy simply, and we have to find what the ground state is. So as we change mu, the kind of atoms self-organize into whatever the lowest energy configuration is. Okay, so that's a self-organized magnetic chain. Okay, so then if we take that, then we can calculate actually. So for example, the top two then are plots then as a function of delta and mu along the y and x axis of what the best pitch angle is q and the difference between the rungs delta q. Right? So actually delta q you see on the right hand side there, just here, that is often either 0 or pi, right? Once mu becomes large, actually we kind of reach the top of the band, and these methods don't work so well. This is why there's noise up here. But otherwise, it always seems to prefer these configurations. Q, the pitch angle, also kind of varies around in various different ways. But actually, the interesting regions are these ones down at the bottom, because if we calculate the invariant, so here the invariant nu, we see that these are the regions which are topologically non-trivial. Right? And this bottom left plot is actually the kind of what the actual ground state energy is for all of these different cases. Okay, so let's take a note actually of the symmetries that we have here, right? So this is a topological superconductor. So we always have particle hole symmetry. We have a time reversal symmetry, but not the usual one, fermionic one. We can actually also have a fermionic-like time reversal symmetry, but actually it exists in the rungs, right? And it only exists when this pitch angle between the rungs is pi. So at those points, we have this kind of additional symmetry, which actually means that we have sort of too many symmetries, because out of these two anti-unitary symmetries, we can make a unitary symmetry, and we should then block diagonalize our Hamiltonian. Right? So this actually plays into some of the results a little bit later. And of course, we have the chiral symmetry. The chiral symmetry is the combination of the time reversal and particle hole symmetry. Right? So this is everything that we have here. And as I said, we can calculate then the appropriate invariant, right? So it's just this winding number here. And you can see you get these two different regions where it's 1 or 2. Now, actually, in these two different regions where the invariant is 1, this corresponds to delta q equals 0, but where the invariant is 2, it's actually delta q equals pi. So what we actually have there really are two copies of a chiral system, okay? And that's why if we calculate this kind of overall invariant, it tells us 2, but strictly speaking, one should say that the topology corresponds to two copies of a topologically non-trivial system. Okay, let's take a kind of cut through this and see what happens then. So here then on the right-hand side is the kind of lowest energy states for an open ladder, so with open boundary conditions on the end as we go along this black arrow. And in the top here are given the energies, so the red and green hashed regions, so these are the kind of non-trivial regions. We actually note that the gap does not close as we move in and out of many of these transitions. Okay, so we get the boundary modes forming as they should from the bulk boundary condition correspondence, but we do not get a gap closing, right? Moreover, actually, the symmetry properties have also not changed. Okay, not those relevant for the topology. These remain the same. And actually, we can see that from, if we look then at what the Q and delta Q are actually doing, what we see is that there are discontinuities actually in Q as we cross these boundaries, right? In all except this last one at the end here, just past mu equals 3. Okay, so what we in actual fact have is we have a topological transition which is driven not by gap closing, not by symmetry changes, but actually by a first order transition in the magnetic order. Okay, so that's the kind of main message that we have here, that actually, in principle, if you allow the wider degrees of freedom of our system, which are, really there, and you see what happens, and you include them and see what happens, then actually you can get these kind of what we call unconventional topological phase transitions, where there's no gap closing and there's no symmetry change, but actually something else is kind of shifting in the model, and actually here it's simply a first order magnetic transition. Okay, thank you very much for your attention.